topic I chose to speak about is on the volume-based equilibrium calculations, not necessarily because I think they are better than any other way of doing the calculation, just because almost by chance throughout my career, I started doing work that was related to this type of application, and then all of a sudden I had, of course with collaborations, developed so many tools that they started to converge to some applications, and these are the applications that I'm going to talk about today. And I'll begin with, let's say, with the basics of why this type of calculation might be important, and I would begin with a tank. Suppose you have a storage tank, and you know the volume of this tank, you know the temperature of this tank, assuming that the temperature is uniform throughout the tank, and you know the component amounts, so how much of each component is inside the tank. And then you might be interested in trying to figure out many properties, calculate many properties. First of which, the number of phases, and I emphasize the number of phases because it will be important for the discussion of stability analysis in a few minutes. Then also I would like to know the amount of each phase, the composition of each phase, the volume of each phase, and I might be interested as well in calorimetric properties like the enthalpy of the phases, internal energies, and so forth. So this is the most kind of basic version of a volume-based calculation that might be of practical interest. But not only this one, where else it matters. For example, if you have a tank, but now this tank is leaking, so there is a leak from this tank, and in a situation such as this one, in addition to knowing the properties of the fluid within the tank, the same properties as we discussed before, the phase amounts, volumes, compositions, and so forth, you also want to know the same information for the fluid that's leaking from the tank. So if I want to do a kind of forecast of what might happen during an industrial accident, information is very important. I want to know the flow rate and the composition of what's leaking. So to do that, in addition to solving a flash TVN flash, I also need other properties such as the thermodynamic sound speed, and I need a flash with specifications of entropies, amounts, and stagnation enthalpy, and I'll come to that later on. Where else it matters? For example, it matters when I'm trying to do compositional grading, depending on the approach that I take. And again, if I think that I know the volume of my, say, reservoir, the temperature, assume it's isothermal, the component amounts within it, and I know the height of the reservoir, I can now account for the effect of gravity and calculate again the number of phases. It's in principle, I know the phase volumes and the amounts in phase compositions as functions of height, as function of level, function of position. So in a problem such as this one, in which I have specifications of temperature, volume, and component amounts, what say basic thermodynamics tells us is that the equilibrium condition, the state of equilibrium, can be calculated by minimizing the Helmholtz energy compatible with the internal constraints of the system. Of course, the internal constraints play a role. If it's free, so there is no membrane, nothing, then it will just be a kind of phase equilibrium with specifications of TVN, and I can solve this problem by minimizing the Helmholtz energy. But the problem of minimizing the Helmholtz energy is normally solved assuming that there is a certain number of phases. And if you make the assumption that I have, say, 2 phases within the system, then I find out what distribution of the components and of the phase volumes will minimize the Helmholtz function. But it's not always the case that I know how many phases exist. In some cases it's trivial, in some other cases it's not. And then for many years now, say, phase equilibrium calculations embed the phase stability test. And in the case of the Helmholtz, and we can derive this phase stability test using different thermodynamic potentials. So the Michelson's work in 1981 used the Gibbs energy, but you can replicate that type of derivation using other potentials. So you can start with entropy or internal energy, or in the case here in terms of an expansion of the Helmholtz energy. So the problem is whether I can start, say, with a one-phase system and then split it in a yellow phase and now a small amount of a green phase, but conserving the volume. So I now have a constraint that the volume of the original system and of the system after partition, these volumes have to be the same. And this leads to a formulation of the phase stability test based on the Helmholtz energy. If I have a way to minimize the Helmholtz energy and I have a phase stability test, regardless of the mathematical details of the implementation of each of them, I can start thinking about putting these things together, these elements together, and create some useful tool. As, for example, a Flash algorithm that would minimize the Helmholtz energy, accounting for the possible inclusion or exclusion of phases. And the way these calculations, and now it's the traditional way of doing these sort of calculations, you start with a number of phases. I put here 1 because if you have a system with chemical equilibrium, you need to minimize the Helmholtz energy for a single phase chemical equilibrium. If you do not have, then you don't need to minimize the Helmholtz energy for one phase system because there is no alternative. But so either way, what happens next? So if you start with one phase, you test the stability of the system, the thermodynamic stability. If the system is unstable, so you add a phase to the system and you repeat the exercise of minimizing the Helmholtz energy. And when you do that, especially when you're doing calculations close to phase boundaries with systems with more than 3 phases, it's necessary to test for the possibility of eliminating a phase and this leading to a decrease in the thermodynamic potential. So normally we think about the phase equilibrium problem, minimization of Helmholtz energy, and the phase stability test, but there is a kind of a little brother here called the phase elimination procedure that needs to be tested every now and then. So if we put these to work then, and we have very good and reliable numerical methods, I can solve a problem with specifications of temperature, volume, and phase amounts. So as we move through this presentation, my goal is not to go deep into details of the numerical implementations, but rather to highlight some points that would lead to the applications. The title had to do applications, and this will be my emphasis, not so much on the numerical details, but we can discuss them later on if there is any specific interest. So now on calculating phase stability based on the Helmholtz energy, so what you can do is basically replicate the way it was done by Michelson for the Gibbs energy in the 80s and account for the fact that you need to have volume conservation. So remember, the volume of the single phase and the two-phase systems have to be the same. So you have to account for volume conservation. Then you have a phase stability function that is the difference of the chemical potential of the incipient phase, the trial phase, minus of the phase that's already present, times the amount in the incipient phase, but also you have this contribution that comes from the pressure difference. Now, regardless of the fact that you specify T or T, V, and N, or T, P, and N, if a certain state is unstable, it's unstable, regardless of the specification you made. So in terms of identifying whether the system is unstable or unstable, doing the way that is shown on this slide or doing like Michelson did and proposed years ago, you get exactly the same answer. You have to. If you don't, it's because something is wrong. Because regardless of the specifications, if a system is unstable, it is unstable. So what is the point of doing the way I suggested is that the phase stability test in a flash calculation plays two roles. One is decide whether it's stable or unstable. This is the most obvious one. But then there's a second, there's a bonus when you do this, which is to generate good initial estimates for the calculation with two phases. And if you have good initial estimates, you are sure that you are going to avoid trial solutions. Or, sorry, not trial, non-trivial solutions. So you're going to avoid trivial solutions, so you'll get non-trivial solutions for sure. So this is the point of doing the way it was done. So the mathematics or the numerical trickery that has to be used in the phase stability test, I think, in my opinion, it's even more rigorous, or it's trickier than in the phase equilibrium calculation, because if you do the phase stability right, then you eliminate most of the problems you get from the second part, which is the minimization of the Helmholtz energies. So you need to ensure that you get the minimum, the global minimum of the phase stability function. This is easier said than done, because algorithms, minimization algorithms that give you certainty of attaining the global minimum are very costly from the computational viewpoint. So this is not how it was done here. It uses an empirical method, so it's called stochastic tunneling, combined with second order minimization. So there is no guarantee that we will always get the minimum, but there's a good probability that it does. So in this work, what I did was to compare with another algorithm that was published by Professor Firozabadi and his group. And I got near perfect agreement with his results. There is one discrepancy, and the discrepancy is that some of the results that he showed in his paper with his group also have not only transition from 1 to 2 phases, but also has from 2 to 3 phases. So his formulation was focusing on transition from 1 to 2, and when I did it in more general fashion. And for instance, these dotted lines here is the boundary between the two phase is here, and 3-phase region. And this was done not by tracking the locus of these lines, the phase boundaries, but rather by creating a grid. The idea was to test the phase stability and the flash algorithm. So it was not, the idea was not to track this line, but to do thousands of flash calculations within a window of temperature and molar density. And by checking where we got stable or unstable system, and then draw this line. So a plot like this represents thousands and thousands of flash calculations, all of which converged based on this procedure. So this is one example with 3 phases. Here's another one that shows 3 phases. So I just picked up those that had 1 to 2 and 2 to 3 phases as outcome. Now, all of this started because of Rogério Esposito, who was a PhD student with Frederico Tavares and myself around year 2000, 2005, this period, early 2000s. And he, at the time, worked for Petrobras, and as he still does, and he wanted to calculate compositional segregation. And then he became a very well-known specialist in this topic. But at that time, we wanted to do an isothermal calculation, and the way we did it as a TVN flash, and with the effect of gravity. And the way we approached, well, if you have a smooth transition as outcome of the effect of gravity, you need to integrate the value of dA over the whole region. This is essentially impossible to do analytically if you use any realistic or practical equation of state, so this has to be discretized, and this was the approach we took to create discrete layers and add the effect of each of these layers. And then there is the question, is there a vapor-liquid or a liquid-liquid interface? Oops, it was vapor-liquid and liquid-liquid. Mistake here. So that's what we wanted to find out. So we wrote the Helmholtz energy of each layer. We added the effect of gravity to the chemical potential, and we added the effects of all the layers to get an approximation to the Helmholtz energy of the whole system. And then we adopt a dual loop strategy. In an outer loop, we tried to locate the phase interface, and we used a very simple numerical method to do that, like simplex optimization, because we wanted to find out whether we had the vapor-liquid interface, say, at this level, or maybe at this level. And why positioning level interface is so important? It's very important because if the interface falls in the middle of a layer, then the density of this layer will give origin to a negative pressure, for example, and you have an unrealistic pressure profile. So positioning the interface exactly is of crucial importance. And the approach we took at that time was to have kind of two loops. In one loop, we locate the phase interface, and then we discretize, for example, here, we create discrete elements for the liquid, and we create discrete elements for the vapor, and we then use a TVN flash to find out the distribution of the elements within the phases. So, and then when we do this, the minimization, we need the terms of the gradient, of the Hessian, and they were all done with analytical derivatives. And here are some examples that work that we did long ago. So these are the, say, pressure profile with depth. So here is depth, the vertical axis is the depth, and the horizontal is the pressure. So we have very small pressure change with depth in the gas phase, and then when we go across the interface and go into the liquid phase, then we get a much more pronounced pressure change. It looks like it's a straight line, which would be if the liquid were incompressible, but we didn't make this assumption here, just coming from the equation of state as it is. Here, so compositional profiles that we got at that time, so we could calculate the compositions of the liquid and vapor phase as function of position, of depth. And also in three-phase systems, here we have a gas phase, an oil phase, and a water phase at the bottom. So we could calculate compositions, pressure profiles, everything based on this dual loop approach, numerical approach. And this is a calculation close to the critical point, and then you get this kind of smooth transition. This is height against density, smooth transition of density close to the critical point temperature. Now, we had this tool, and there was a paper appeared in Chemical Engineering Science by a group in Shell Research in which they did molecular simulations of gas centrifugation. So the idea was to purify natural gas using centrifugation, and they did molecular simulations. And Fred and I said, oh, okay, we can do it with our program. Let's do it. And we got the results in like 3 days. And so what did we do? So we had a vertical cylinder. Now we have a horizontal cylinder. What changes from one calculation to the other is how the effect of the external field, now a centrifugal field, affects the chemical potential. And off we go using exactly the same idea, exactly the same approach. And the results we got were nearly perfect match with the results of molecular simulation from the Shell Research group. And here, what we see is a pressure as a function of the rotation axis at 70,000 RPM. This is a mixture of argon and ethane, and here we see a point where there is a phase transition, then there is a sudden change in slope of the pressure. The pressure increases much more rapidly because it's a liquid phase from this point and onwards. And we could get composition profiles. So the basic idea of using ultracentrifugation was that you could, in the outer layer away from the rotation axis, you could enrich, get enrichment of the heaviest components, which in this case would be hydrogen sulfide and carbon dioxide, and this is exactly what you see here. So this was a kind of immediate application of the work of Rogério Espósito by just switching from a vertical to a horizontal geometry. And then we got excited and we decided to go beyond hydrocarbons and play with colloidal particles, very small particles of called percol. Percol is used in biomedical separations, and it's small particles of silica coated with a polymer. And when you run a percol gradient, what you do it to separate different parts of cells, organelles. And here I think this picture, I just took this picture as an illustration. I think these bands here are something of color just to show how, depending on the density, the particles get together. They are separated essentially based on density. So we formulated this. Now this time we use an equation of state for spherocylinders, developed by Professor Silvio Canuto of the University of São Paulo. He had just developed this equation of state. We used this one, and it's similar to the problem that for the centrifugation, with this important difference is that we made this calculation assuming we had the Macmillan-Myers system, in which our assumption is that we had a wall permeable to the fluid, to the solvent, in such a way that it had a field of the solvent, and then the solutes were modeled within by means of the equation of state. And because of that, then we had to use an effective mass for the particles, which was the mass of the particle minus the minus the mass of the solvent that would be occupying the same volume, basically buoyancy. And then off we went with these calculations, and these are comparisons of the results from this sort of TVN flash with, again, Monte Carlo simulations. The results for hard spheres here. The results are essentially identical with exceptions at the edges because of edge effects on the Monte Carlo simulation. But in the bulk of the system, the match is essentially perfect. And this sort of bending that occurs in experiments, here we did a simulation. This is particle numbers against distance from the rotation axis. And here is the particle number of the percol particles, the particles that form the gradient. And here are different particles with slightly different densities and how they would create peaks. And that's exactly what we see. Now we cannot compare quantitative. This is just a picture that I took yesterday when preparing, so there is no quantitative comparison, but there is a qualitative comparison that you get peaks according to density. And the least dense particles, the spread is larger. It become more focused, narrower distribution as the particles become heavier. Everything just makes sense. Now, this program was used for many years, and then in 2016 it became so complicated to make changes because so many people had worked on it, including myself, and it was really difficult that we decided to have a new beginning in 2016. So we wrote an entirely new code for volume-based calculations, allowing for multiple regions. So I have, for instance, a pore or porous materials, and I have a pore size distribution. I can say pore of type A is a region, pore of type B is a region, and so I can have this sort of flexibility with dynamic memory allocation for different regions, different components, any number of external fields, more than one field in a given direction, and fields in perpendicular directions as well. And we were megalomaniac at that time, and we called the program Mega TVN, the name by which it goes to this day, even though reality has shown that it's not so powerful as it was originally intended, but the name remained. So first work with this was with Professor Yannis Economou and two Master of Science students, and so this was kind of a picture of what we had in mind, the ability to, say, have as for example here, let's say the white region is a bulk fluid, and I have a green pore, and I have a red pore, and I have three regions, and the program can handle them all, including the possibility of having a, say, gravity along with the effect of an external wall. And we can account in this development, we account for replicas. So we have, again, a pore size distribution. I have a certain pore, and I have, say, 10 to the power 6 of that pore, and then another pore, I have 10 to the power 5. So I have a different population of pores. All of this is accounted for, all these possibilities. But again, is the idea of adding the contributions of discrete layers of the Helmholtz, discrete contributions of the Helmholtz function over layers and now over regions. In our work, we used Peng-Robinson volume translation, and we considered two types of fluid wall interactions and gravity. And just, this is not actually what the program is meant for. It's not meant to be a replacement for molecular simulation, absolutely not. There are several limitations and severe limitations to doing that, but this kind of gives the qualitative idea of what the type of result we get. So it gets kind of internal profile within the pore, and again, not meant to be a quantitative comparison, but it kind of gives the right trend, points in the right direction. Now, what it's meant for is to compare macroscopic properties, and here this slide compares the results of this program with density function theory results from Professor Firozabadi and his group, and the agreement is very, very good. This is a very fair comparison in the sense that we used the same model, Peng-Robinson volume translation, and the same fluid wall interaction potential, which in this case, I don't remember, but I think it was the still potential. And just for the sake of illustration, in this calculation we did, in this particular plot is a result in which we used fluid wall interactions, we used gravity. So we had two fields acting on the system at the same time in perpendicular directions. And here is the molar concentration profile of methane and CO2 as a function of depth. And here is, again, not meant for quantitative comparison, but for qualitative comparisons only. Here is the internal profile, internal mole fraction of CO2 within the pore as a function of distance from the wall at two different depths. So here we see the effect of depth and height, depth and confinement together at the same time. More recently, we extended this work using the Saft-Jahmy equation of state, and we have made comparisons with systems in which we took into account pore size distribution, so the ability of taking into account several regions. And here is just an example of what we get for the absorption of CO2 on activated carbon compared to experimental data. Now, let me move on to applications to process safety. And process safety is a very broad subject, very interesting, that goes all the way from applied psychology to try to understand why people take safe or unsafe actions at the workplace and in their daily lives, but also includes very technical subjects. And in particular, I have been working with Professor Luc Vechaud from Texas A&M University for a number of years on fluid releases from pressurized vessels. And there are two situations. You may intend to do that if you are opening a relief valve. So you have an overpressure and you want to open the valve to the vessel to relieve the pressure, or that it may be an accident, an industrial accident. Either way, trying to understand what happens when there is a fluid release from pressurized vessel is a very, very interesting problem of practical importance. Now, what I'm going to show you are some results and kind of somehow the Lego bricks that went together into the simulation of venting and leaks from reactive and non-reactive systems. And the first thing that's not necessarily easy or obvious is to find out what phase is leaking. And my drawing skills are terrible, I'm sorry for that, but I think this image still conveys the message. So suppose yellow is liquid and white is vapor, and let's say at the beginning of a leak, you have a leak from the liquid phase, in this case, and then as material leaves the vessel, there will be an interval of time in which you have leaked from both phases at the same time, and after a longer period of time, the leak will be from the vapor phase. And this has a dramatic impact on the composition of what's leaking and the flow rate of what's leaking. Well, in a vertical cylinder, it's very easy. There is a relationship between volume of liquid and level is very simple, because the volume is the area of the basis times the height. Not so easy when you have a, say, horizontal cylinder, because the cross sectional area changes as the level changes, or when you have a horizontal cylinder with hemispherical or toroidal caps. So the relationship between volume and height is not that trivial. In some cases, you need to do numerical calculations. If you have the volume, you want to have the height, you need to do some trial and error, some Newton Raphson, some calculation to find it out. It's not necessarily trivial. Anyway, here what we did was first to formulate a mass energy balance for a leaking tank. And let's think that the green streams are, say, the normal operating streams, one feed and two normal outputs, and then there is a leak, which is the red output. Well, I need to do a mass balance on a molar basis, so it's the flow in minus flow out, and if I have reactions in the system, and there is a reason for why this is very important or very useful, now I need to account for the rate of reaction. So I need to write a molar mass balance for each component, a differential balance, and an energy balance, again accounting for the enthalpies of the streams coming in and the enthalpies of the stream going out, and eventually some heat load. And specifically here, I put the kinetic energy term in the outstreams because they may be very important. Not so much so for the regular streams, but for the accidental leak, it's very important, as I will comment later on. Now, again, what I need to do is to integrate a set of differential equations. I cannot do this analytically for the most practical cases, but the integration will give me at each moment in time the values of the internal energy, the components amount, and the volume is fixed. So I know U, V, and N. So if I assume that the properties within the tank are uniform, I have to solve a UVN flash, a flash that requires entropy maximization. I'm not going into the details of this calculation, but this was something that I worked on in 2008, 2009, and this came out as a publication, Fluid Phase Equilibrium. Another thing that I need to worry about is the leak flow rate. And the way it was modeled in this conventional model is to assume that the leaking point is at steady state and it is a converging nozzle, converging adiabatic and isentropic nozzle. And if this is the case, then the enthalpy of the fluid inside the tank has to be equal to the enthalpy of the fluid that leaves the tank plus the kinetic energy. And assume it's isentropic, then I have a problem in which I have an enthalpy specification, I have an entropy specification, and this is a flash with specified values of stagnation enthalpy, which is summation enthalpy plus kinetic energy, stagnation enthalpy, entropy, and component amounts, is an HS flash. Because we had that problem, then we set out to develop an algorithm to do that. And just to, again, I'm not going to discuss the details of the algorithm, but I may have two situations here. I may have a subsonic flow, or I can have a sonic flow. So this is energy balance, this is entropy, mechanical equilibrium, and this is phase equilibrium, equal chemical potentials. And if I have a sonic flow, now the kinetic energy would depend, of the output stream depends on the sound speed. And the output flow may not have just one phase, it may have more than one phase. So this throws the need for another algorithm, which is an algorithm to calculate sound speed in systems that have more than one phase. So it is like a chain of things that you need to put together to simulate a leak from a tank, such as those that we are trying to do. So off we go, and to calculate sound speed in multi-phase systems. And in a single phase system, what you need to do is to calculate the change of pressure with density at constant entropy. But in a multi-phase systems, the volume is the summation of the phase volumes, the entropy is the summation of the phase entropies, and the amounts are the summation of the phase amounts. And this creates a huge chain of manipulations that you have to carry out in order to calculate these derivatives. So it takes quite a few pages to show the equations that need to be solved, but it can be done, and it works pretty well. It's very interesting, and the interesting things is that the sound speed may have kind of these abrupt changes, and the algorithms capture these very well. And these changes are the outcome of the fact that the compressibility of the system changes dramatically when there is or there is not a vapor phase in the system. So here are just some illustrations of this fact. Now, all of this had to be put together: UVN flash, HSN flash, sound speed calculations for multi-phase systems. And when we have all of this together, then we can go back to the fluid releases from pressurized vessels. And here are some results. This is just air, so there is just one phase, air, release of air from tanks. The simulations are the solid lines, and the dotted lines are the results of experiments. Here is a rather complicated calculations based on an industrial accident happening in Italy, called the Via Reggio accident, in which a train wagon capsized and leaked. And of course, because it was an accident, there is no experimental data as such for the accident, but other people tried to model this, and we compared our results to their results with excellent agreement, and we calculate how the temperature, how the pressure changed over time during the leak. And the leak was initially from a liquid phase within the tank, and then afterwards, because the liquid level was lowered, and then at the end it was from the vapor phase. Here what I show you is time against flow rates. So here, for example, take this line, the flow rate of each component as it leaks from the system. So here it's leaking from the from the liquid phase. So the flow rates, they decrease, but not dramatically. And then at this point in time, then it becomes a leak from the vapor phase, and then the depressurization takes place very rapidly, and the flow rates decrease by orders of magnitude very rapidly. So all of these we could kind of simulate with our program of our process safety simulator. Now, I mentioned that reactive systems were very important. The reason why they are very important is because certain materials, and this is peroxide, DTBP, ditert-butyl peroxide, this is used as in polymerizations, and these substances are very tricky, because you may leave them and almost nothing will apparently happen, but this reaction here that forms acetone and ethane is an exothermic reaction. So if this decomposition starts, then you produce, your products are much more volatile than DTBP, and the temperature increases. So if it's not controlled, this is what you experience in your vessel. So an exponential increase of temperature and of pressure. Here is the pressure curve. And very easily you can have an industrial accident if you don't take action. So this is this simulation here was compared to experimental data, very nearly perfect agreement. And here is a simulation of what happens when you have a relief valve in your system. So the relief valve opens, and the moment the relief valve opens, so here we have examples of 3 situations opening at 0.4 megapascal, 0.45 and 0.5. And then if you have a valve of the correct size, then you kill the reaction. So essentially you kill the reaction because you discharge the reactor completely. Now, if the valve, the relief is not designed properly, you may have a situation which decreases, then it increases again. So that's why it's important to get it right. Now, this, if you look at these curves here, it looks as if it's just killing and just kind of vertical line down. Here we have magnified, now this is temperature, not pressure, but temperature just a few seconds after the opening of the valve, and I have no way of telling whether this actually happens or not. But in terms of kind of the intricacies of the calculation, it's fascinating, because here the first leg you have 2-phase flow, and here it's wrong, it's 1 phase, and then this point of minimum up to here it's 1-phase flow. And at this point, there is a transition from sonic to subsonic flow. So very complex behavior here. Again, I have no way of telling whether this actually happens or not. Probably, I would say probably not, because in real life in an accident, this is a very messy situation. It's not as well behaved as the assumptions we have made, but we had to make assumptions to move on. Now, final set of examples, it has to do with supersonic separators. And because we had all these tools that I mentioned together, we could go into the simulation of supersonic separators. What are they? They are a piece of equipment in which, say, you have a feed from the left, so it's a gas, and it goes into a conversion nozzle, and then as it reaches the throat, if the conditions are right, it should be at sonic speed, and then as it expands into the diverging section, it becomes supersonic. And because the kinetic energy increases so much, the enthalpy has to go down because of energy conservation, and this causes a decrease in temperature and partial condensation if you have, say, a contaminated natural gas. So the heaviest components will typically condense, and you can design a kind of output to collect the liquid, and you have a purified gas at the exit. So the claimed advantage of the people who design and sell these things is that they are compact and they're useful for inclusion in platforms. Petrobras, for instance, has an interest in this type of device. Now, if you want to analyze this device, I put the equations here, but no worries, I'm not going into the details. You need to analyze first, to take some kind of big look at what's going on. And here what I have is, this is mass balance, these are enthalpy balances, this is entropy. And you need to do this section by section, between the entrance and the throat, and then between the throat and a side stream, the position where you have a side stream to remove liquid. And then inside this equipment you normally have a shock wave, so you need to model the shock wave. The shock wave is not isentropic, and then after the shock wave, so at the shock wave you need to use the momentum balance, and then after the shock wave it's isentropic again. So you have HSN flashes almost throughout the whole piece of equipment. So it's a playground for HSN flash calculations. Now, the way I initially did it, the first work of the series was to take the length of the device and discretize it the way we discretized compositional grading and the effect of gravity or centrifugation. So just create discrete elements and get the profiles. And these are the results of the dotted line here and of the blue curve. So these are the results of kind of slicing the device horizontally and solving these equations point by point. Now, if you have a piece of equipment like this in a process simulator, say you want to add this to Aspen, for example, you don't care necessarily about the internal profiles. Perhaps at the end, but not in the middle of the calculation. So what we set out to do more recently was to modify our procedure and just calculate the key points that are necessary to get the output conditions. And these key points are the condition at the throat, then the conditions at the shock wave, and the conditions at the exit. So by doing this, we could save a lot of computed time. So here are examples. This example has no side stream. This example is the effect of the side stream location on the conditions of the outputs. So we could do a lot of things much, much quicker than we could do before. So just examples of this is Mach number, sound, speed of sound inside. So the fluid velocity as divided by the sound velocity at each given position. And here, just a composition, how the composition changes between the feed and the gas that comes out for a given situation. Kind of approaching the end, so what is my current work? I'm working with Frederico Tavares and a student, Túlio Freire, on phase behavior of fluids confined within small geological formations. I'm working with Luis Franco from Unicamp and André Gonçalves, PhD students, on the behavior of confined fluids under the effect of gravity, revisiting that problem and going deeper into it with some kind of deep questions, at least to us, as to kind of trying to understand several things. We are working on liquid swelling inside these tanks and these process safety calculations. When you have, so the tank opens, there is bubble formation, and the liquid kind of rises because it's liquid plus gas inside the phase. So this has an impact on the rates of the releases. We are modeling this. We have a student just defended a thesis last week. We gave a kind of partial answer. We're not entirely happy. We expect to do some progress in the coming months, and we are working on uncertainty in the design, effect of uncertainty on the design of supersonic separators. So these are topics that are somehow related to what I presented. In addition to those, I'm working on the simulation of pressure retarded osmosis, a technique to recover mechanical power from desalination plants, and is an application of equations of state for electrolyte solutions. Also, I'm collaborating on an European project on the development and application of equations of state for electrolyte solutions, and I'm working on the modeling of separation units for the production of cannabis derivatives. The people. Now, quite often we see presentations with a picture of everyone of a group. Now, what I presented here is the outcome of more than 20 years of work, and it's just impossible to mention everyone. What I would like to say is that I remember each and every one of those projects and of the people that worked on them, and I'm sincerely grateful for their collaboration, which was essential to accomplish what was shown here today. Some final and random thoughts on the challenge of using complex models for the applications I have shown. And I would like to illustrate these with what I call the IKEA syndrome. IKEA sells furniture, and you go to the shop and you see this, let's say this piece of furniture, and it is useful, it is practical, it works well for what I need, and I want it. And I buy, it comes, I take it home in a box, and then I'm faced with the challenging of put it all together. And when I come to this point, then I need to think, do I really want it? Now, if we look at this plot, beautiful representation of the volumetric independence of hydrocarbons from the work of Lafitte et al. And it's useful, it's practical, it works well, and I want it until I take the paper from Lafitte et al. And these are part of the equations, probably at least an equal amount of equations, if not twice as much, to implement that. And then I ask myself, do I really want it? Now, in all fairness, I am guilty as charged. If I look back, my own papers mostly fail at presenting information in a easy to use way. So I am not doing better than anyone else. And in fact, it's the example I took from the paper of Saft Yami is to a large extent unfair, because they did an excellent job of trying to make life easier, because they have an appendix with all the equations that are necessary to model it, but not necessarily in the way to use. So everyone, and I have talked to many people who have implemented SAFT-VRB, still it takes a lot of time to navigate through the jungle of formulas. Complexity will not go away. We model complex phenomena. We should not expect our equations to be simple. They will not be simple. They will not be simple. What we need to do, I think, is to make a better job at communicating what our model is. And I think we do a pretty good job, mostly, in terms of presenting the model so that people can understand how the model is built or the logic. I think it's great, but I think there should be ways, maybe these, nowadays there are these papers in which you can add something like supplementary material, like a guideline, step by step, how to implement these very complex models. I think these would be very useful. So I know I have an editor of fluid phase equilibrium here in the audience, and I think this should be something that here is a suggestion. My personal workflow, for a number of years, I try to understand the model to the best of my ability. I try to understand how to program the model, but for many years I have not programmed models myself. I just use computer algebra to do that. And I think that if you know how to use computer algebra, especially for the young people, so if you spend some time learning how to use Mathematica well, Maple well, it pays off. It's an initial investment of time, but it will make your life much easier further down the road. Thank you very much again for the invitation, and thank you very much for attending my presentation. Thank you all.